Team Food Bank, and we did a project on improving the operation of warehouse cold storage areas. At least that's what our initial focus was. And I'm Nafis Ahmed, this is Shay Raminian, this is Pablo de Santiago, and that's Prejal Bangura. And we're just going to continue with our presentation.
Okay, I'm going to give you a bit of the background. North Texas Food Bank actually established their business in 1982 as a nonprofit organization. Their goal is to have a hunger-free world. Also, during the first year, they provided 400,000 meals. Last year, they provided 37 million meals. And their goal is to provide 50 million meals by 2011.
I'm going to take you over through a brief overview of how we went over this project. First of all, we went to the North Texas Food Bank and we met with the director of operations, Sean Gray, and we had a brief tour of the facility. After that, we sat down with Dr. Barr and we actually thought that the business that Food Bank was running was pretty efficient, but there was still scope for improvement in two areas. The first area being that they were coming up with a new inventory system, so they had to improve on their IT department. And the second was that the freezer and cooler could be more efficient than it was actually. We went with the second option. We looked at the freezer and the cooler, and we had some observations. On the second time we went there, we saw that we observed the food coming from the trucks to the freezer and the cooler, and we saw the storage process, the labeling and the sorting out, and we measured the time and other stuff, and we collected data. So we thought that the main metric to measure improvement in efficiency would be time, as there was a lot of wastage prior to that. And finally, we used a simulation model to help us make the system more efficient. These are some of the pictures. This is the freezer and the cooler, and yeah.
Labeling system.
Yeah. This is the freezer, and this is the cooler. After that, we looked at some of the problems which are occurring at Food Bank. The first one was the biggest problem, their organization of items, which was the most critical problems, and this was the reason which was causing the time waste. Because the item, when a forklift comes into the freezer, it has to move around items in order to get the specified items, so there's a lot of wastage in time to get into the item needed. And the items like meat and other beans and stuff, they have more demand. But they were kept in front of the freezer. So what they need to do is take them. They were kept at the back. So what they need to do is take them and keep them in front. Whereas demand for blueberries is less, so it needs to be kept at the back. The usage of the limited space was a big problem, and there were some problems which were going unnoticed, and they needed someone new to look over it, because the people working at the food bank were really familiar with the place, so they weren't looking into any of the problems which were existing. Finally, the agencies had to wait a long time in order to get the food required, so there was a lot of wastage in that too. Some of the data we collected was organization, but we didn't receive any cycle time, and there was plenty of inventory data available, and we went to the food bank and we timed the process and observed other things.
Alright, this first picture that will come up here, I don't know if you guys noticed, we took this picture a few weeks ago, and I just want you to notice this is an item that's in the freezer. It's called blueberries. They have a huge amount of blueberries, and I just want you to notice the date received is September 22nd, 2009, and as of a few weeks ago, and as of right now, it's still there. And so, I'll touch on this product, I'll touch on this a little bit later, but you know, one of their problems is limited space, limited quantities. So, I mean, this is one of the underlying problems, having items that have been sitting here for, I mean, 7 months or so. So, I'll touch base on that a little bit. This is inside the cooler. As you can see, this corner of the cooler, it's all kind of horizontal. There's no vertical space. In every other cooler and freezer, they have a lot of shelves, but for some reason, this corner they don't have vertical space. And so you can imagine if a forklift's trying to get something, it has to move other items out of the way to get something in the back, and then move the items back. So it's very unorganized. It's a little, you know, it's a little hectic, a little chaotic whenever forklifts have to go in. And then the final picture, this just kind of shows in the freezer they have a lot of meats come in every day from different places. These meats are basically, they're the local grocery stores. They're kind of almost about to expire meats. So they come in and they get sorted. That's just kind of the process.
And for the situation analysis, we actually spoke to the operation manager, Sean Gray, and we also talked to the facilities manager. And they actually told us about the problems that they have with their cooler and freezer. And as Prajwal said, because we were the outside viewers, they wanted our opinions that they can improve their system. Their layout is actually consists of 2 different docks, east and west. The east dock is usually for the trucks to deliver and pick up foods, and also during the afternoon they receive food. And the west dock primarily is for the agencies to come and pick up food.
Now I'm going to speak about our observation and investigation stage a little more. Basically, after talking to Mr. Gray, we went and started speaking with the facilities manager, got some input from him and his ideas, and also to learn, his ideas of what might be a problem, and also learn how the system itself works, the process of receiving, and basically anything that goes in and out of the cooler, where it's coming from and where it ends up. We also spoke with some of the workers, such as the forklift employees, the receivers, the truck drivers who drop off the items, and then who also deliver as well. And also the agencies who for the most part, take about 2/3 of the items that come into the freezer or cooler. And we came up with this flow chart here, which, as you can see, it begins with they basically go throughout the area, pick up these frozen items, frozen and cold items. They get delivered to the east dock. From the east dock, a forklift receiver gets them, labels them, and then weighs them. And after being in the weigh station, goes to the freezer cooler. From the freezer cooler, it can end up going to a couple number of locations. It can be used in the kitchen, in meal preparation, and if it goes into the kitchen, it ends up being moved back into the cooler and a different form. It can go to, for meat specifically, they go to a sorting station close to the kitchen, and then get put back in the cooler. And from the cooler, more than 2/3 of the items get picked out by the agencies. And the other third gets sent out the truck routes in the morning to other locations throughout the Metroplex. And from our analysis, we can see, we confirmed that basically North Texas Food Bank runs a very efficient operation. In fact, they're actually ranked number 1 in Texas for pounds of food produced per square footage. They're also number 8 in the nation out to about 200 food banks. So they run a very efficient operation. And our investigation and observation confirmed this. So we figured that our recommendations might not be one single big recommendation that would change things drastically. Instead, our best approach was to recommend a number of recommendations, a few recommendations that hopefully add up to some kind of tangible results. And we kind of based that on the Kaizen method in Japan, where they basically look for a number of wastes, such as waste of motion, weighting, waste of storage space, transportation waste, and from there we able to make our recommendations. Hope that they add up to, like I said, tangible results. From this, we ended up creating a simulation model from a flow chart and especially focus on the items that end up with the agencies, they get picked up by the agencies because the agencies take up most of the items that, most of the product that ends up in the freezer cooler end up going to the agencies. So, as you can see, they arrive at the docks, they get weighed at point one, and we base it on a frequency interval of basically 20 minutes intervals throughout the day, 15 minutes. The items that get put into the freezer cooler will be based on probability distribution, and it's done on random. And the item waits for a given amount of time. Once again, it's done based on probability distribution. And then the item is moved to the weighing station, from which it will get delivered to the customer in the queue. And please will speak more in depth about our model.
Okay, so before I touch base on this, I just want to say exactly how the process for how the overall process kind of affects us with the cooler freezer operation. So usually how the food bank customers operate, there's an online ordering system that they can go into and order food, dry food, frozen food, refrigerated food, and usually the food's ready and packed before the agency comes the next morning. And however, with the cool foods is, oh, and I should mention that the agencies come, whenever they come, they sign in, and it's a first come, first served basis. So whoever comes first gets their food first. And but however, how it affects the cooler and freezers, like those foods from the cooler and freezers that they order, they're not taken out of the docks and the fridges until the agency actually shows up. Because the agency might not show up, if they bring food out, there's a risk of it spoiling. So that's kind of a limitation that the food bank has to wait until the agency actually shows up in order to bring the food out. So what ends up happening is this line gets so long because of the first come, first served policy that whenever they try bringing foods out, it's in a time of a lot of stuff going on. So that's where we notice the problem. And secondly, our simulation, we use Pro Model, and we try to model the food bank as accurately as we could. So you can look at our model at the top. The area with the 5 trucks represents the delivery dock where they actually get the product. There's a weighing point, so the food goes to the first weighing point, and then it's taken by forklift, and it's taken by forklift to one of the freezers or the cooler, and then from there it's ordered and then it's brought back to the queue and the waiting point, and then finally goes out. And so here, this is where we defined our location. So within Pro Model, we didn't actually have to define variables like you do in a code. It's kind of you define locations, which are basically like variables, and you can set the constraints or the capacities through the program itself. So this second column here, where it says cap, you can set the limits of each variable. So and we set the times of everything just based off of our observations from going there. And so the model here, it has arrows pointing out, and that's just kind of like our process flows of how items move from one place to another. And we use expected values from historical data, so we got a lot of inventory data. We got imagine 22 pages of 10-point font, top to bottom. It's an entire year's worth of everything that moved to a food bank, and the weights, the quantities. So we actually had to rigorously go through everything, sort out what would be applicable to our situation. And then based on that, we determined what percentage of foods come into the cooler, what go into the freezer, and created like a uniform distribution. And then the program here, it determines a random number, and based on the random number, it determines whether or not where the food's going to go. If it's type 1, it's going to go to this. It's going to go to cooler. Type 2 will go to freezer. Just to accurately model the simulations as well as we could. We looked at their online ordering system. We looked at agency sign-in sheets to see the frequency of timing in. Like when they sign in, they write their times. If you guys are interested, you can see it in our documents and appendices. And also, finally, we performed an ABC Pareto analysis. I'm going to go over quickly what that is. It's basically you classify items as class 1, class 2, class 3, or class A, class B, and class C. Class A items are items that there's not a lot of quantity, but they constitute a lot of the activity. So for instance, you might have a class A item would be like 20% of the inventory, but 80% of the revenue. Class C would be something like 50% of the inventory, but only 5% of the revenue. Based on that, we classified items such as meats, high turnover items as class A, low turnover items such as blueberries, as you saw, it's been sitting there for like 7 or 8 months now. Those is class C. And so, based on those, values, we're able to determine realistic probabilities. Next slide.
Maybe close it down.
Huh?
Time's up.
Oh, it is. Well, basically, through our simulation and our recommendations, we just showed that the main bottleneck, it lies within the agency queuing. It's not within the freezer or the cooler, how many shelves they have or how many receiving docks they have. It's within the queuing because of the first come first serve basis. They have to go. It really limits and constrains the food bank and their operations. So, it's unfortunate we didn't get to finish, but if you guys are more interested, you're more than welcome to look at our PowerPoint or document. And we have a few recommendations here. I'll just run through them real quick. Like I said, we determined it's probably the line. So we recommend looking into waiting line queuing theory for the North Texas Food Bank, recording cycle times, opening up another dock for specific for another line, and grouping items together in the food coolers and freezers. So.
And adding an extra shelf for
Yeah.
space.
Then they can reach their goal of 50 million
Yeah.
meals batches on level. Thank you.
Thanks.
Thank you.